The first question we would ask ourselves, why we have so many viruses? Do we have so many emerging viruses? Starting from 2003, SARS, and then 2005, and 1997, starting from Hong Kong, the first H5N1, it's a bird flu, and then 2012, MERS, then 2014, Ebola, and 2014, Ebola, and 2015, and especially this year, we have already over 20 imported cases in mainland China. So, and then you have Zika. So what's the next? Why do we have so many? So make sure everybody is focus with me. I want to show you some really funny slides. First, because it's climate change, El Nino phenomenon. You have all these climate ecological changes, so that leads to El Nino and it made the whole climate change. That's made the virus to emerging. And also human behavior. Go back home today, check what you wear. So this is the whole evolution of our underwear. It's true because ecological change, and you need to go follow with to make sure your behavior will match what happened with the ecology. The good example is flu. Why we have H7N9? Especially in mainland China, in Canton and in Shanghai, in Eastern China area, because previously, for example, H7, how we have the H7N9. H7N9 is a typical avian flu. So it used to be, it's harbored in the avian, including chicken. Now it must be there, but because of the development of the Pudong, everybody knows the Pudong development area. So there you have a wetland. That area, a wetland, usually we don't have that many people there. You don't have domestic animals, don't have human there. There's migratory birds. They will stop over there. But now you build up so many skyscrapers, so many people living there, because once you have people settled down there, you have domestic animals. Especially in the eastern area and southern China, people like to have the freshly killing birds. So then you have that's the change. But I give examples. Since you occupy the niche for the migratory bird, we have to change our behavior ourselves. For example, because of that, maybe we have to stop eating all those freshly killed birds, but we don't change our behavior like that. So we still consume those freshly killed birds. So this is why I give a very good example. Either you stop to occupy the niche for the wild animals, that's ecological or climate change, or we change our behavior. For example, in China, I'm calling Southeast Asia and including Hong Kong, stop consuming those freshly killed birds, and then change your behavior. Maybe you are okay. So that's a very good example. So then the virus and human beings, what we are doing. So the virus itself try to adapt to the human beings. So I will give you an example. So, if someone working on the evolution, they give you a very good example how the virus evolved and what's the key determinant for the pathogenicity and the virulence. I will give example in terms of host jump for the adaptation of the receptor body. For any animal virus, they need to find a receptor or molecules on your cell to get into the cell. So today I will focus on how, of course, I think it's some other people come here to talk, it's quite complicated. It's not one factor, but I want to address one of the factors is important, is the receptor body. The virus are screening their receptors to get into the host cells. So this is a host adaptation and virus stability. There's also balance. I think we are living in the world, we are doing balance, everyone here, sitting here. The virus itself, they need to keep the identity of the virus. Ebola must be Ebola. Ebola is not a flu, but they need to keep their stability. They also need to adapt to the new hosts. A good example I want to give you, this is the work we done when we were in Sierra Leone. So you remember when Patrice Sabati from MIT and Harvard, they published a paper in August 2014. They collect the data in Sierra Leone in May. Those sequences of the viruses, they got a conclusion. Might be the evolution, the mutation rates for the Ebola virus might get faster than the historical Ebola virus. That means the virus is getting adapted to the human beings quickly. So that, when you have a Guinea virus as a reference or index, you can see through the time, I call this one as a shower chart. This shower chart, when you have a shower, all this water coming down. When you get to the bottom here, you have more and more mutations here. But there are always plateau. Once you get in a stage, the virus will be fixed. But this figure tells you in the index, Guinea, started from Guinea. The Guinea virus down from May to September to November. So gradually, the virus adapted to, to the new host or whatsoever you can call it. But you can see gradually mutations is here. So that's a positive evidence for the adaptation. So as I mentioned, I want to focus on one of the factors would be the virus adaptation or virus try to find its new niche, new host for the receptor binding. They need a receptor to get into your cell. So my work, my lab, suppose you have this antigen-presenting cell, or it's just a cell, and you have the virus, all those undeveloped viruses there. So once they need to get into this cell with a receptor. So in this interface, you have the virus interaction with the host cell. So my lab has interest for the interaction in the protein-protein ligand interaction in this interface. So once a virus gets into your cell, and the protein can be processed, could be proteasome dependent or independent, processed into peptide presented by the MHC or HLA, and then you have a T cell to target this. Some viruses like HIV or MERS, they can directly infect. Again, here, your interface, you have a lot of protein ligand or protein interaction, especially nowadays. Protein and carbohydrate interactions are getting more and more important. This my lab also started to evolve this kind of work because started with the flu virus with the salicylic acid binding. So in this interface, some viruses like HIV or MERS, they can directly affect your T cells. So this is we also introduce this interface interaction.